Welcome back. Today, 6.3, Uniform Convergence and Differentiation. This will be the second and final section of Chapter 6 that we look at. In the earlier section, 6.2, we looked at sequences of functions and we focused on the continuity. Here, in this example, instead of continuity, we'll consider differentiability. So really, there's just one main theorem in this section that we're going to focus on, and then I'll do several examples kind of thinking about that theorem. And the big question is, if a sequence of functions approaches a limit uniformly, and if each term of that sequence, if each fn is differentiable, must the limit function be differentiable? All right, let's find out. So recall from section 6.2. Suppose I have a sequence of functions that approaches some limit pointwise. If each individual function, if each term function is continuous at a point C, then the limit function need not be continuous at C. And we had an example of this, a nice example which was x to the n. There's the limit function, and each fn is continuous at the point 1, but the limit is not continuous at 1. However, and this was sort of the big point of 6.2, suppose that my functions approach the limit with uniform convergence. Well, in this case, continuity holds. If each fn is continuous at C, then the limit is continuous at C. This is the continuous limit theorem. So here's a new question. Suppose that a sequence of functions approaches f with uniform convergence. If each fn is differentiable at C, must f be differentiable at C? And the answer is no. Sadly, no. So consider this function fn. It has this kind of weird looking definition on -1 to 1. It turns out that it approaches the absolute value function. So it actually starts off as an x squared when n equals 1, but then as n increases, it gets closer and closer and closer to the absolute value. Now, the derivative of this function has this form, and if we look closely, this derivative is defined at 0. I can plug in 0 and the derivative makes sense. And the value of the derivative is in fact 0. It is differentiable at 0. So every one of these term functions fn is differentiable at 0. Here's a GeoGebra example. Okay, so here is our sequence of functions. When n is 1, n is 2, 3, 4, 5. So it looks like they really approach the absolute value. I can go back. N is 1, and then when n it gets bigger and bigger and bigger. But it turns out that even though, see, n is 13 here, even though it looks like there's a sharp point at the origin, actually no. If I were to zoom in, then it would end up having just a little bit of a scoop, like an x squared at the bottom, and have a derivative that's 0. So it actually doesn't have a point. It's flat at the origin, but very subtly so. You have to zoom in really far. I don't know how long I want to take on this. Okay, you have to zoom way in until you see the curve flatten out, but it does. Okay, so every one of these functions is differentiable at 0, but the limit function, absolute value of x, is not differentiable at 0. So, no, unfortunately, the answer to that question is no. But perhaps this raises a new question for us to answer. How to strengthen the hypotheses to guarantee that the limit function is differentiable? It's not enough to require that my sequence approach with uniform convergence. Is there something else, something additionally that I can require that will guarantee that the limit of this sequence is differentiable? Here's the idea, and this brings us to the differentiable limit theorem. If a sequence of functions approaches its limit pointwise, and the sequence of derivatives converges uniformly to something, then the limit of the derivatives is the derivative of the limit. So instead of looking at the sequence of functions and requiring that my sequence of functions converges uniformly, I'm going to look at the sequence of derivatives and say, does the sequence of derivatives converge uniformly? So it has to converge to something. It doesn't even really matter what, but let's just call this G. So my sequence of derivatives converges to G. Then the limit of the derivatives, that's the G, the limit of the derivatives, is the derivative of the limit. That's my f prime. So f prime is going to equal G. Here's the official statement of the differentiable limit theorem. Suppose a sequence of functions approaches its limit pointwise on the closed interval from a to b, and assume that each fn is differentiable. If the sequence of derivatives converges uniformly on the interval from a to b to a function g, then two things happen. One, the original sequence of functions converges uniformly. That's interesting. We didn't require that. All we required initially was pointwise convergence. But if the sequence of derivatives converges, then the original sequence of functions converges uniformly. And secondly, the limit f is differentiable and its derivative is g. Now is probably a good time to take a minute, pause the video, read through this theorem a couple times, and see that it makes sense. One small note, this isn't exactly how the book states Theorem 631. In fact, point number 1 here comes from Theorem 632 in the book, but it's nice to, I think, put them all together in one statement. All right, at this point, let's look at several examples showing us the ideas behind this theorem. I will not prove it. I just really want to take today's lesson to focus on the examples and think about this relationship between sequences of functions and differentiability. So I'll go through 3 examples, and down below here I have rewritten the differentiable limit theorem, so it's handy to look at as we go through our examples. So again, the big idea, if a sequence approaches its limit pointwise, and if the sequence of derivatives approaches a limit uniformly, then the original sequence, in fact, approaches its limit uniformly, and its limit is differentiable. And the derivative of its limit is the limit of the derivatives. Okay, example 1. Suppose my function looks like this on -10 to 10. Well, symbolically, as it's given right now, it's a little hard to kind of see what that looks like, but at least I can probably figure out where it's going as n goes to infinity. Simply take the limit as n goes to infinity, and we find it approaches x over 2. Let's take a look at that in GeoGebra. So here's our example 1, and as n goes to infinity, it looks like it's approaching the straight line y equals 1/2. Now, it is approaching this on all real numbers, but we're just going to focus on the interval from -10 to 10. So that limit, the x over 2, we're going to call that thing f. F is the limit of our sequence of functions. Does my sequence approach this limit uniformly? At this point, we're not sure. By taking the limit as n goes to infinity, I just figure out pointwise convergence, but I don't know anything about uniform convergence. But we can look at the derivatives and use those to help us. So at this point, look at the sequence of derivatives. This looks like 1/2 plus x over n. And pointwise, taking the limit as n goes to infinity, this will make this second fraction go to 0. It looks like just 1/2. So the sequence of derivatives approaches 1/2. So I let g denote the limit of that sequence of derivatives. Here we are. I'll show the sequence of derivatives. So I start off with n equals 1, and the derivative is just this nice straight line there. N equals 2, 3, 4, and that sequence of derivatives looks like it's approaching the constant value of 1/2. Here's the claim. The sequence of derivatives approaches 1/2 with uniform convergence on -10 to 10. So how do we prove that a sequence approaches its limit with uniform convergence? Well, I need to take the absolute value of the difference between the function and its limit, fn prime of x minus 1/2, and I'd like to show that it's less than or equal to something that doesn't depend on x. So can I show that this is less than or equal to something, and I don't want the x to be in there? Well, here's where I use the fact that x is bounded from -10 to 10. So, in fact, the biggest that x could possibly be is 10, or the lowest -10. The biggest that the absolute value of x could possibly be is 10. So, in fact, we can write that this guy is less than or equal to 10 over n. I've found a bound that does not depend on x. And this helps us figure out how we should choose our big N. Okay, so here's the remainder of the proof. Let epsilon greater than 0 be given. Choose a big N strictly greater than 10 over epsilon. Now, if little n is greater than or equal to big N, so I'm thinking at some point in my functions, I've made my little n big enough so that my functions are way down the line, then the difference between f prime of n and 1/2 is less than or equal to 10 over little n, less than or equal to 10 over big N, which is strictly less than epsilon. And so this proves the claim. So in fact, our sequence of derivatives does approach its limit with uniform convergence. Well, what does that tell us? By the differentiable limit theorem, the original sequence approaches its limit uniformly. So up here, I asked the question, does Fn approach f uniformly? Now I know, by the differentiable limit theorem, the answer is yes. And I know something more. That derivative, the derivative of the limit, is actually g of x. So the derivative of the limit, f of x, is g of x. So just in case you weren't sure that the derivative of x over 2 is 1/2, now we know it from the differentiable limit theorem. Let's look at another example. Example 2. Consider this function x raised to that weird power. This is actually the one that we looked at before, where the function does approach the absolute value of x uniformly on -1 to 1. So I won't prove the sequence approaches absolute value of x uniformly, but let's accept that for now and move on and see what else we can determine. How does the sequence of derivatives converge? So here's the example. Recall, here's my sequence of original functions. It starts off looking like x squared, and it merges into what looks like absolute value of x. And now let's look at those derivatives. Here's the derivative in the orange. And as n increases, you see that my derivative is still continuous, but it goes through 0. Continuous going through 0. And as n increases, my derivative becomes more and more extreme. It looks like -1 for any value, for any x that's negative, and it looks like +1 for any x that's positive. And it's going to have a value at 0 also, because all of these derivatives go through 0. Here's the symbolic expression for my derivative, and you can work this out symbolically, that if x equals 0, then the limit of these derivatives is 0. If x is greater than 1, then the limit of that derivative is +1. And if x is less than 0, then the limit for any x, this is independent of x, the limit of the derivative at any x will be -1. So there is the limit of our derivatives, which we call g. And so g has the form where it looks like this. So here's a question. Does the sequence of derivatives approach its limit uniformly? What do you think? And the answer is no. And there are a couple good reasons. The sequence of derivatives can't possibly converge to g on -1 to 1 uniformly, and here are two good reasons. The first one is based on continuity. Each derivative is continuous at 0, but the limit is not continuous at 0. So let's think about our continuous limit theorem from 6.2. If each term function is continuous, and if the sequence converges uniformly, then the limit has to be continuous also. But the limit is not continuous. And so even though each individual function is continuous, I know for a fact that this convergence can't be a uniform convergence. There's another good reason that uses the differentiable limit theorem, and it goes like this. If my sequence of derivatives approaches its limit uniformly, then by the differentiable limit theorem, f would have to be differentiable at 0. But we know that the absolute value of x is not differentiable at 0. So these derivatives can't approach their limit uniformly. Okay, so that's another way of using this differentiable limit theorem. We didn't really set it up as here are our hypotheses all satisfied and then use the conclusion of the theorem, but I could argue by using the differentiable limit theorem that I know that this sequence of derivatives does not converge uniformly. All right, one more example. Consider a function that looks like sine of nx over n on the real numbers. Here's the function, and it looks like sine, but as n increases, it shrinks down smaller and smaller and smaller down to what looks like the line 0. So pretty clearly, the limit of this function as n goes to infinity, the limit is just the line 0. Now something curious is happening with the derivatives. Even though the function is squeezing down to 0, those slopes actually don't squeeze down to 0. The slopes remain at +1 and -1. The sequence of functions approaches 0 on all real numbers. Here's our first claim. This sequence, the sequence of original functions, actually approaches 0 uniformly. Okay, so let's go through the little proof. I take the absolute value of the difference of a term function minus the limit function, and we end up with the expression absolute sine of nx over n. And what is my goal? My goal is to show that this is less than or equal to something that does not involve x. It is independent of x. And do you see what that is? This expression is less than or equal to 1 over n. Independent of x. So that allows me, given an epsilon greater than 0, to choose a capital N. So let's say capital N is greater than 1 over epsilon. If little n is greater than or equal to big N, the absolute value of the difference is less than or equal to 1 over little n, which I had before. Less than or equal to 1 over big N, which is less than epsilon. Done. So yes, in fact, my sequence of functions does approach 0 uniformly. Now, let's consider the sequence of derivatives. As n goes to infinity, does this sequence of derivatives, cosine nx, does that converge to a function? So in orange, there is my sequence of derivatives, and look what happens as n goes to 2, 3, 4, 5. The derivatives, that's the orange function, it doesn't approach anything. It just kind of squeezes in like an accordion into the origin. Well, horizontally, but not vertically. It doesn't approach the 0 function. It doesn't approach any kind of trig function. It just kind of keeps on changing and changing and changing. It just does not approach anything. And you can see how this reflects the idea that my blue function, the original function, even though its values are shrinking vertically down to 0, its slopes never actually change. As seen by the derivative always stays from -1 to +1. No, this limit of derivatives does not exist. Here's the lesson. Uniform convergence of the original sequence, and even the differentiability of the limit of that sequence, so 0 is very differentiable, that tells us nothing about the sequence of derivatives. So my f is really behaved as nicely as I could hope. It approaches the real numbers uniformly. It has a limit, which is 0, and 0 is differentiable. But despite all those nice things, the sequence of derivatives behaves very poorly. In particular, what this shows us is that the converse of the differentiable limit theorem does not hold. Take a look at the DLT here on the left. I have satisfied the conclusions of the theorem, that my original function approaches its limit uniformly, and that my original function has a nice derivative. However, the sequence of derivatives does not approach anything nicely at all. All right, these are the big ideas: uniform convergence and differentiation. Take some time, work through these problems, read through that theorem again and again and again, get a good feel for it. Just a few problems this time, 2, 4, and 6. Give those a try, and here's a little bit of algebra help just to remember and maybe help you through problem number 2. All right, go to it. Good luck. Ask as you have questions.